operations. Operations on fuzzy sets. There are several operations that are possible on fuzzy sets. There are several operations that are available for regular sets or crisp sets and fuzzy sets. So what you know definitely from, let's say, general set theory is the union and the intersection of sets, but also the complement of a set. What is new for fuzzy sets is the so-called support and the height of a fuzzy set. So we will discuss that now in a little bit more detail. As I said, for regular sets or crisp sets, we have the following standard set operations. If we have subsets A and B being subsets of some universe X, then we define the union and the intersection of we define a union and intersection of two sets in a standard way, as you know from basic mathematics. The union are all those elements that are either in A or in B or in both. And the intersection is defined as those elements that are in A and in B. And the complement of a set are all those elements of the universe that do not belong to the set. So that would be the complement of A, all those elements of the universe that are not members of A. That's the standard definition of union, intersection, and complement in classical set theory. Now, for fuzzy sets, we have what we call the support. The support of a fuzzy set is the set of all those elements that have a membership degree greater than 0 to a fuzzy set. So when we would, for example, jump back to our Excel that we just looked at, and we would say, what is the support, for example, for the fuzzy set short? So it would be all those elements of the universe that have a membership degree greater than 0 to our class short. So you can see it would be, if we look at short and at the membership values, so it would basically be all those elements from 135 to 179. All those have a membership degree greater than 0. So those elements here those individuals who have this corresponding height of between 135 and 179, they all would be the support of our class short. So all those elements that have a membership degree greater than 0, that's called the support. And here you see the formal definition in mathematical terms. Now, what is the height? The height of a fuzzy set. The height of a fuzzy set is the largest membership degree in the fuzzy set. If we have a height of 1, then we call a fuzzy set a normal fuzzy set. Now again, let me jump back to our example here. And let's stay with the class short. So what is the highest degree of membership here? Well, it is 1 because, it's 1 because we have here the membership of 1 for several elements. So this is the highest degree of membership. So the height of our class short, or of our fuzzy set short, is 1. As I should say here, not every fuzzy set has a height of 1. We will see that later on, and we look at some examples of union and intersection. And in particular, when we later use our examples with GIS, when we have to overlay several fuzzy sets to compute some final result of a fuzzy set. And in here, the membership is definitely not always 1. So if the highest membership value in a fuzzy set would be 0.8, for example, then the height of that fuzzy set would be 0.8. Now that is what is called the height of a fuzzy set. And again, if the height is 1, then we call a set normal. Later on, also, we will see that we can normalize what we call normalize every fuzzy set, meaning we can make a fuzzy set to a fuzzy set that has at least 1 membership degree that is 1. So that means normalization of a fuzzy set. We will learn that or hear about that later on. The procedure is very simple. You just divide every membership value by the height of the original fuzzy set, then at least you have 1 element that has a membership value of 1. But we will talk about that later on. So that's the height of a fuzzy set. Then we can define when are 2 fuzzy sets A and B, when are they equal? Well, 2 fuzzy sets A and B are equal if for every element of the universe X, the corresponding membership values to A and to the set B are equal. So if for every element of the universe, the membership value of A is the same as the membership value of B, then we call these 2 sets equal fuzzy sets. Another operation corresponding to the to the subset concept in classical set theory is called the inclusion of a fuzzy set A in a fuzzy set B. If we have a universe and we have 2 fuzzy sets A and B, then we say fuzzy set A is included in fuzzy set B if and only if for every element of the universe X, the membership value of A is less than the membership value of B, less than or equal, of course. So in a graphical way, we could look at this situation where we have a membership function for A in blue and 1 for B in red. And we can see here that all the membership values of A are less than the membership values of B for every element of the universe. So the set A is included in the set B, or it's a fuzzy subset of the fuzzy set B. These are some operators on fuzzy sets. And now we can look at the important operations of union, intersection, and complement of fuzzy sets. So let's first start with the union of 2 fuzzy sets. In classical set theory, you know, the union is defined in a very simple way. The union of 2 sets A and B are all those elements that are either in A or in B or in both. This is one unique definition, and that's the definition of union. What we see here is that for fuzzy sets, we can define a union in different ways. I show you here 3 different definitions of union. All 3 can be used and are a representation of the union of fuzzy sets. And depending on your, let's say, depending on your model or depending on your project, you might decide which of the 3 representations for union of two fuzzy sets you might use. The results are not the same, but they are similar, as you will see in a moment. So the simplest and the easiest way of defining the union of two fuzzy sets is to use the so-called maximum operator. So if we have two fuzzy sets A and B, and we would like to calculate the union, the membership value for an element X of the union of these two sets A and B, we just take the maximum of the membership values for a particular element of the universe. So this maximum operator is the simplest way of computing the union of two fuzzy sets. But as I said, there are other options that we can use, and I show you here two more that can be used to compute the union of two fuzzy sets. So one operator is calculating the union by taking the sum of the membership values minus the product of the membership values. So you see here the sum of the membership value for A plus the membership value of B minus the product of the membership value of A and B. So this is another way of computing the union of two fuzzy sets. And the third one is using the minimum of 1 and the sum of these two membership values for A and for B. Now, you might ask now, yes, but how can we guarantee that the membership value is always between 0 and 1? Well, in fact, it is very easy to show that for all three of these operators, the membership function of the result is always between 0 and 1, because, you know, the membership value is between 0 and 1. So if we have for both a membership value of 1, then we would have the maximum of 1 and 1, which of course is 1. If both are 0, the maximum of 0 and 0 is 0. And if one of them is 0 and the other one is 1, the maximum of 0 and 1 is again 1. So never any other value as 0, never any other value outside the range of 0 and 1. And even if it's 0.5 and 0.5, so anyway, or 0.5 and 1, so it is always between 0 and 1. And also in these cases here, if we take the extreme and say, for example, that the membership value for both are 1, then we would have 1 plus 1 minus 1 times 1. So 1 plus 1 is 2, minus 1 is again 1. Or in this case, the minimum of 1 and the sum. So again, in the extreme case that both would be 1, then we would have the minimum of 1 and 2, and again, the minimum is 1. So this is an option, or these are three options to compute the union of two fuzzy sets. In the next slide, I show you diagrams of the union of fuzzy sets, and I used as an example the set for the fuzzy set for short and average, as we have had in our previous example. And here you can see the result of the union, or let's say you see the membership function of the union when you use these three different types of computing the union of two fuzzy sets. And you can see they are different. So this shape of the membership function is different from that and different from that. So, but they are all in a way similar and a valid way of computing the union of two fuzzy sets. Now, what we can do is, and we will do that after our break that we will have very soon. I will show you the same, how we can compute that using Excel, for example, as a way to calculating the union and the intersection of membership functions. Now let's look at the intersection of two fuzzy sets. Again, we have three options here that are relatively straightforward. The easiest one is the minimum operator. So take the minimum value of the corresponding membership values of the two sets. This is the easiest and simplest intersection operator. Use the minimum. There are two other alternative operators. One is taking the product of the membership values, just the product of the membership values. Sometimes this operator is also called soft intersection. So sometimes in literature you will see the term soft intersection for fuzzy sets, meaning using the multiplication operator, multiply the membership values. And the third one is taking the maximum of 0 and the sum minus 1. So again here, since all our membership values are between 0 and 1, the resulting values are also always between 0 and 1, because again, when we take, for example, here the extreme case that both membership values are 1, in that operator we will have the maximum of 0 and 1 plus 1 minus 1. So that would be 2 minus 1 is 1. So the maximum of 0 and 1. And again, it will be 1. And in this case, with the multiplication operator, since all the values are between 0 and 1, and if we multiply two numbers that are between 0 and 1, their value is always between 0 and 1. So if it's 1 and 1, so 1 times 1 is 1, 1 times 0 is 0, 0 times 0 is also 0, and let's say 1.5 per 1.5 is 0.25. So it's always between 0 and 1. And of course, with the minimum operator, it's the same case. It's always between 0 and 1. So we have here the three options for calculating the intersection of two fuzzy sets. And again, here you see the example with our classes short and average, and how the resulting membership function for the three different types of intersection will look like. Now, as I said, we again can look at these using our Excel, and I show you on the next slide. Assuming again we have a spreadsheet where we have a table with the height of persons, and then we have the classes short and average with the corresponding membership values. We can implement these operators using a formula in Excel. And again, there are this would be the translation into Excel using here the cell values B2 and C2 for short and average. Then, of course, for the union, the maximum operator would be expressed as the maximum of the two values, or the second option, the sum minus the product, or the third option, the minimum of 1 and the sum. And for the intersection, we have it in the same way. We can use the minimum operator, minimum of two values, the product of the two values, or the maximum of 0 and the sum minus 1. So again, let's look at our spreadsheet, and let's look at our union and intersection operators here. So what you see here is I have copied from the previous sheet the height and the membership values for short and average, as you can see here. And now we can use the calculations for union and intersection. So for the union, we could use now the maximum operator, meaning using the maximum of both values. Okay, wait a moment, I made a mistake here. The maximum of this and that, so, and of course, filling it down. So that would be now the result of the union of the set short and average. Then we said a second option could be to use the sum minus the product. So let's go back. The second option is using the sum. So this plus that minus the product. And again, filling it down, which gives us this representation of the union of these two sets. And finally, the third option, taking the minimum of one and the sum. So taking the minimum of one and the sum of the two values. Okay. Which will show us. Okay, now what we can do is we can. So this. This is now our first, taking the maximum value. This is our second option for the union. And this would be the third option for the union. As you can see here, they are all a little bit different, yet similar, and both of them are representing the way to calculate the union of two fuzzy sets. Now we can do the same thing for the intersection of two fuzzy sets. For the intersection, we said the simplest operator is the minimum operator. Take the minimum of the two values. So my Excel is frozen. That's strange. Okay, now I'm back. Okay, we said the simplest way for the intersection is taking the minimum operator. So let's take the minimum of the two values. And let's see how that looks like. Okay, that would be the minimum operator for the intersection of these two. Then we said the second option would be taking the product of the two membership values. So again, let's take the product. Which would look like this. And the third option, taking the maximum of 0 and the sum minus 1. Taking the maximum of 0 and the sum minus 1. Which will give us this example. And again, we can now look again. That was the first option. That was the second. And that was the third. So we can now display all three of them together. And again, you can see here, they are different, but yet in a way similar, and both of them are valid intersection operators. A small remark here on the side for later on in this class, we will discuss fuzzy reasoning, meaning we will be using rules and data and fuzzy sets, and from applying the rules to the fuzzy sets, we will come to conclusions. So rule-based systems using fuzzy sets. There will be a need also to compute a sort of intersection, and in this case we will mainly use the minimum operator for the intersection, whereas in the geographic examples using geodata, we will mainly use the multiplication operator for computing the intersection of two fuzzy sets. The reason why we will use the multiplication operator, I will explain also in a slide coming up. There is a particular reason which we will then call interactive and non-interactive operators, but just wait a moment and I will explain that soon. Now, what we have learned so far is how we can calculate union and intersection of fuzzy sets. And of course, let me just go back once more to our spreadsheet. And of course, the height of a fuzzy set that we discussed before the break, you remember the height is the greatest membership value in the fuzzy set. Also, the height can be computed very easily. For example, if we want to know the height of our intersection, and if I just jump back to the intersection and take the multiplication operator as our example here. So the height of this fuzzy set would be, I will calculate it here, would be, of course, the greatest membership value of the fuzzy set. So it would be the maximum of all those values here in our multiplication operator for the intersection. And that, of course, would be, I have to make it, of course, bigger, otherwise you can't read it. The maximum of this would be, okay, now I have my row height is a little bit bad here, so let's make it bigger. So the value is 0.3. So 0.3 would be the height of this fuzzy set represented by that membership function. So you see here we have a fuzzy set where the height is less than 1. But that is, as I said, that's no problem as long as we know how to compute the height of a fuzzy set. So it's 0.3. And of course, we could make the fuzzy set to a normal fuzzy set by dividing every membership value by the height. Then, of course, for at least for the 0.3, we would get a value of 1, because if we would divide this by 0.3, then of course the result is 1. Anyway, this is another, let's say this is just a brief explanation how to compute the height using Excel. That's very easy, just take the maximum value of the membership values of a fuzzy set. Now, since we know now how to compute intersections and unions of fuzzy set, let's move on to a next operator, which is called the complement of a fuzzy set. The complement of a fuzzy set is defined as take 1 minus the membership value of the elements of the universe. So to compute the complement of a fuzzy set, you just need to compute 1 minus the membership values. And again, I have some graphical example here showing you the fuzzy set average and how the complement of average would look like. And in the same way, we can do it ourselves here. We could, for example, go back here to the to our original example, and I just move this diagram. Move these things a little bit to the right. So that we can, for example, here compute the complement of, for example, average. So that would be just 1 minus the membership value of average. So you have here. And then when we go down here, that would be now our complement. And what we could do is we could, for example, add this and add our values. Okay, and then this would be average, and that would be the complement of average. So you can see here, that's pretty easy also to calculate what's the, if once you have a fuzzy set, you can easily compute the complement of a fuzzy set by just taking 1 minus the membership values. Okay, let's continue here. Now, we know from mathematics that there are several laws that can be applied to sets and set operations. Now here we have some properties that are valid for both fuzzy sets and crisp sets. So fuzzy sets and traditional classical sets, for both of them, these properties are valid. For example, the so-called idempotent law, which just says if you compute the union of a set with itself, it doesn't change the set. And on the other hand, if you take the intersection of a set with itself, it also will not change the set. So this is true for both regular classical sets and for fuzzy sets. The same is also true for the so-called commutative law, meaning it does not matter in which order you apply union and intersection. So A union B is the same as B union A, or A intersection of B and is the same as B intersected with A. So the order is irrelevant. It is both true for crisp and for fuzzy sets. Also the associative law, where you have the union of A with the union of B and C. Again, here it doesn't matter in which order you compute the union and the intersections, it will be the same result. So that again holds for crisp and for fuzzy sets. Also the distributive laws, where you basically distribute one operator into the brackets where you use another operator. So A union B intersection of C is the same as A union B intersected with A union of C, and the same holds for the intersection. So this so-called distributive law is also valid for classical sets and for fuzzy sets. In the same way, the double negation holds, which basically would also be a double complement in fuzzy sets. So the complement of a complement is the same. So if you take the complement of a set, it doesn't change the set. This is basically what it says here. In logic, it would be called double negation. In our sets here, we would call it the complement of the complement or the double complement. And finally, the so-called De Morgan's law are also valid for both fuzzy sets and for crisp sets, meaning the complement of the union of two sets is the same as the intersection of the individual complements. So, in other words, complement A union B is equal complement of A intersected with complement of B. And of course, the same holds if we have the intersection operator here, the intersection, the complement of the intersection of A and B is the same or equal as the union of complement of A and complement of B. So these laws or these properties are all valid for both crisp sets and for fuzzy sets. These two here, the so-called law of the excluded middle and the law of contradiction, are only valid for crisp sets or classical sets. The law of the excluded middle says A union A complement is the universe. So if you take a set and you take its complement and you take the union of these two, of course, you get the whole universe. And the law of the contradiction means A intersection complement of A is the empty set. So if you take a set and its complement, and you take the intersection, of course, this intersection is empty. So, but these laws are only valid for classical sets. They are not valid for not valid for fuzzy sets. You will see that in one example, and we can also verify it then using our Excel example. So here you have again the fuzzy set average height that we used in our example before. And when you take here, for example, the union of the set and its complement, then you get this membership function as a result. In fact, the set united with its complement should always give will always give the universe in traditional set theory. That would mean there would be a line here at 1, it would always be 1, but it is not. There are other values here that are not always 1. So this law does not hold for fuzzy sets. And also this law of contradiction, that A intersected with the complement of A should in classical sets always be the empty set or corresponding to the 0, but in this case it is not so. So in fact we can verify that using our example here. So let me just go back to the and let's compute the example we have here the complement of average, and we could say the intersection of the complement and the set. So we took average, and we could take the intersection, meaning the minimum operator, for example, of average and complement of average. So then we can show that on our diagram. I just write something here. Okay. And then you can see here, this would be the intersection of the set with its complement. In classical set theory, it would always give a 0, but in our case, it does not, because this does not hold for fuzzy sets. And in the same way, we can use our the union of the set and its complement. And we use, for the union, for simplicity, we use the maximum operator. Let's use this. So, and here again, you can see that the union of the set and its complement in classical set theory would always give you a 1, meaning it's every element of the universe belongs to it. But in our case, we get different values. We get here different membership values that are not equal 1. So this law that the set and the union of a set and its complement is the universe is not valid for fuzzy sets. So you can see here it is pretty easy to verify these laws by using simple calculations in Excel. Now let me go back to the slides. Okay, and then I mentioned before there is a term that sometimes is used, interactive and non-interactive operators. So what does it mean? The minimum and maximum operator for intersection and union are called non-interactive, whereas the other operators, for example, using the product to calculate the intersection of two fuzzy sets, or using the sum operators for calculating the union of two fuzzy sets, they are called interactive. Why are they called interactive or non-interactive? If we take, for example, the minimum or the maximum operator, it could happen that one of the two fuzzy sets is completely ignored. In that case, for example, when we jump back, in that case where we would have one fuzzy set that is completely included in another fuzzy set. So if we would take here, for example, the union of set A and B and take the maximum operator. So we would take the maximum of the two values. Let me go to this. And so what we would do, for example, we have here an element of the universe. So we would take the membership value to A, and we would take the membership value to B, and we would take the maximum of these two. So which of course would give us this value here, but it doesn't really matter what the membership value of A is, because that A actually will never be used. It could even look like this, or it could look like that, or it could be even 0. So it would be really irrelevant what the membership value to A is, because only the values of B would count here for this union operator. That's the reason why they are called non-interactive. On the other hand, if we take the product operator, for example, to calculate the intersection, then the result is the product of the membership value of to A and the membership value of B. So both values go into the result and determine the result. So they interact in a certain way, and that's the reason why they are then called the interactive operators. So on that slide, you see the explanation in different words. but that's the major the difference why some operators are called non-interactive and others are called interactive. So as I also mentioned before, in most of the applications, when we will use fuzzy sets in GIS, we will use the interactive operators for union and intersection, and it's mainly intersection that we will use because the intersection operator basically corresponds to the overlay function in GIS. So when we have a GIS and we are looking for areas that have both characteristics of one layer and the other layer, what we do is we calculate the intersection, or we calculate the overlay of two layers, and that corresponds to the intersection of two fuzzy sets, two fuzzy layers in our GIS application. And for this intersection operator, we will use mainly the product operator or any other interactive operator, rather than the minimum operator that we might not use. Of course, we can use it, but we will most likely use the intersection operator. Now, there is one more thing in terms of operators that we need to discuss for fuzzy sets, and that would be the so-called alpha cuts or alpha level sets. An alpha cut, okay, I just see here in that slide, it's called alpha, which is the Greek character, and somehow it got lost here. I should change that. And of course, you will get an updated version of the slides, as I mentioned, because there are 2 slides missing. So it should be this, and that, of course, should also be the Greek letter alpha. Okay, now it looks better. So, an alpha cut or alpha level set are all those elements of the universe that typically belong to a fuzzy set. So how is it defined? It's defined in such a way that you say an alpha level set of a fuzzy set A with a certain value alpha are all those elements of the universe whose membership degree is greater than or equal to alpha. So, simply speaking, all those elements of the universe that have a membership value greater than or equal alpha belong to that alpha cut. Greater than or equal, if we only allow greater than and not equal, then it's sometimes also called a strong alpha cut. So there's a slight difference between alpha cut and strong alpha cut. Usually we would say alpha cut allowing greater than or equal. And if we say, no, it must only be greater and not equal, then we might call it a strong alpha cut. So again, here there is a simple example. You have here a universe and an alpha value of 0.6, and all those elements of the universe, so the universe is here on this axis here called U, all those elements that have a membership value greater than 0.6, and in fact it's this range here, all those elements of the universe belong to that 0.6 cut. Now, again, we can go back to our spreadsheet. And for example, someone has a microphone on. Could you please turn your microphones off? If we if we, for example, look at an alpha cut of, let's say, 0.7, meaning all those elements of the universe that have a membership degree greater than or equal 0.7 belong to that alpha cut. And if we take, for example, let's take for a moment the class short, then we would look at all those members, all those elements of the universe that have a membership degree greater than 0.7. So it would be this here. Because here you see that here we have 0.67, then 0.63, and so on. So we are decreasing, and only those members, it would be the members with a height of 159 down to 135. Only these elements of our class would belong to the 0.7 cut or to the 0.7 level set. So with these alpha cuts or alpha level sets, we can somehow narrow down our results to those elements that really or typically belong to our fuzzy set. Because if we say, for example, a membership degree less than 0.5 is not really relevant for our result, because the membership degree is too low. So we might only be interested in those that have a membership value greater than 0.8, for example. So they belong much stronger or much more to our fuzzy set than those that have a membership value of less than 0.8. So again, later in our practical examples, we will also make use, or we can make use of these alpha level sets when we do, for example, our fuzzy site analysis, an analysis that I showed you in the first class, taking some regions or areas with certain criteria. And we will do that with fuzzy sets. And then we could say, well, but I'm only interested in those that have a membership value greater than 0.75 or 0.8 to our final class, because for all the others, our membership value is too low. Now, this brings me now towards the end of our class of today.